Alright, good afternoon everyone. We're going to go ahead and get started looking at ionic bonding, and this is going to be a brand new unit. This is actually our sixth unit that we're going to cover this year. And we're going to deal with a lot of the materials that we may interact with on a regular basis. I want to go through a couple of different sections within this unit and sort of give you a preempt or a preview of what's coming up. We're going to look at how we form ions, how we form ionic compounds, and how we go about naming those compounds. First section that we're looking at is, in the end, we want to be able to understand how ions are formed and how to name them. So, ions are going to be formed when an atom or group of atoms loses or gains electrons. But how will we know which situation we're in? How will we know if it loses or gains, or whether it be positive or negatively charged? Now, atoms of metals, specifically, tend to lose their valence electrons. This is going to actually cause them to end up with an imbalance of electrons, more positive than negative charges. This is going to make them overall positively charged, and we call these things cations, as you see here. Now, remember, the number of valence electrons are what we're going to use to determine what the charge is going to be, and I'll talk to you about that in a moment. So, using the example, calcium is in group 2A, therefore it has 2 valence electrons. When it loses electrons, it's going to lose both of those electrons, so it's going to end up with a charge of 2 plus or plus 2. Now, one of the things that sort of helps to govern this is what we call the octet rule. In forming compounds, atoms are going to want to basically be like the noble gases. The noble gases have, for each situation, their s and p orbital completely filled. This is what we talk about when we talk about octet. Why? Because these are the ones that primarily participate in bonding. So, if we're looking at sodium, sodium's goal is to get rid of this single electron here. So let me change the color. It wants to get rid of this electron here. Why? Because once it gets rid of that electron, it can look exactly like neon does. Still being sodium, but now since it got rid of an electron, it's going to now have a positive charge, as you see here down at the bottom. Now, a simple way that we use to show that an ion's been formed is we use electron dot structures or Lewis structures like we talked about before. So, I have my sodium atom. It's neutral, it has no charge, and when it loses its electron, it's going to now be positive. So we have Na plus, showing that it lost the electron, and this is the electron that it lost. This is what we'll usually use as we get ready to move in towards ionic compounds, but we'll keep with this one for just a moment. Now, the other situation that we run into when we form cations is dealing with transition metals. Now, as we know, transition metals are a little different. They don't behave the same way as others do. And so, in order to get what we call a full octet, they're actually going to make their own little bit of a rule. We'll use the example here. We have silver's electron configuration written out before us. Now, the goal is to be like the noble gases, but silver's in a bit of a problem. Why? If it wants to be like krypton, it has to lose 11 electrons. That's a problem. If it wants to be like xenon, it has to gain 7. Now, most times, as you notice, we said that our Lewis structures only have up to 8. And so, this is the reason why. We're actually going to see that it's going to lose electrons in another place in order to get to its octet rule. It's more of a fake octet rule is what we call it for the transition metals. Now, let's look at an example dealing with copper so we can see exactly how this works. So, copper wants to form an ion. So, what it's going to do is it's going to lose an electron from this 4s orbital. Now, you notice as I said, we usually go from s or p orbitals because those are the ones that are going to be most stable, like a noble gas. So, in losing this one electron from the s orbital, it now has part of it a little bit more stable and looking more like, like the noble gas, and it's in its column. Now, notice that it says pseudo. Pseudo is another word for fake. So since it loses that electron, it's going to have a fake stability, I guess we would say. But in a sense, it's going to form the ion that it wanted to. Now, how do we go about naming them? Well, when we deal with metals, it's actually really, really easy. What do I mean? Well, the names of the metals for the regular atoms that we deal with, group 1A, 2A, and 3A metals, is going to be the name of the metal and the word ion. So, if I have Ca2+, it's a calcium ion. Just that simple. Now, what about if we're dealing with copper or chromium or iron or any of those? Because they tend to give a couple different situations. Being that they're transition metals, remember I talked about the fact that they will change up how they do things. They'll change or lose sometimes more electrons than in other situations. So you have to have a way to differentiate or to tell them apart. We do that by writing the name, but then we're also going to add a Roman numeral. So if we look at an example of, let's see, iron. If I have an iron that lost 2 electrons, then what we're going to do is I'm going to write iron, I'm going to write ion, but I have to show that this is the one that lost 2 electrons. So I'm going to put iron 2 in Roman numerals next to it. This tells me that I have an iron 2 ion. Whereas if I lose 3 electrons, iron 3, again Roman numerals, ion is present. Now, again, the Roman numeral in the parentheses indicates the value of the charge. So if I see 2, if I see 1, if I see 5, if I see 20 in that parentheses, I know automatically what the charge is going to be for that transition metal. Now, if the element is non-metal, it's going to gain electrons. And we call this an anion. It's going to have a negative charge, and it's going to be an anion. Now, non-metals gain electrons they need to obtain 8 valence electrons. For example, nitrogen is group 5A. Now, the overall goal again, octet. Octet meaning 8. It has 5 valence electrons. It'll gain 3 in order to have 8. So it's going to have a charge of negative 3. That's what we see here. Now, again, going back to our octet rule, notice here we're dealing with the 3s and 3p for chlorine. Right now, chlorine is just 1 electron away from having a full octet. That's a problem. So, chlorine is actually going to be very, very eager to react and to bond to get that electron so that it can become stable or to look more like argon in this case that has a full octet here. So, chlorine is willing to take on an electron to fill that last part of the shell and then end up with a negative charge to make this happen. Now, this is what we're looking at, and again, this was on the last slide, so you get an idea of where we're going with it, but this is what each of the atoms desires to do. Now, of course, we know atoms don't have minds and they don't really have desires, but in doing this is actually going to make them more stable or lower in energy. And remember how I told you before, electrons are lazy. There's certain things that they're willing to do in order to have that lower amount of energy. Now, just as we looked at for sodium, now we're going to look at the same thing for chlorine. We're looking at our neutral chlorine atom, and we're going to add an electron in this case, and so we'll have a chloride ion. So you notice the ending changed on that. Now, anions produce when atom gains 1 or more valence electrons. There are some situations where there'll be more than one, as we talked about with nitrogen. Now, when we name this anion, I want you to note that it's not the same name exactly as it was before. Now we're going to actually change the ending a little bit. What do I mean? Well, the name of the anion typically ends in IDE, so we're going to change the ending. So, if we have a chlorine atom, that forms an ion is going to become a chloride ion, or oxygen that forms an ion is going to be an oxide ion. We're going to keep part of the base, and then we're going to end it in IDE. This is what we're going to do for any regular anion that we form. Now, this is going to be some of the charges that we find consistently throughout our periodic table. And if you notice, in group 5A, like -3, -3, -3. Group 6A, -2, down the line. In group 7A, again, down the line, all the same charge. So we can start to look at those group numbers that told us the number of valence electrons, and those are also going to help us to be able to identify the charges. Now, in dealing with our good buddies, transition metals, one more time, you want to note that like I was saying before, you want to note that there are actually some transition metals that actually only form one ion, one cation. And so we deal with those in a little different way. When we deal with cations like silver, zinc, and cadmium, we actually don't have to include the Roman numeral. Why? Silver is usually going to be found as silver plus 1. Zinc and cadmium, we usually have a +2 charge. And so you just want to keep those in mind. We're going to do lots of practice with this, so believe me, don't stress over it. We've just actually already talked about this part, so I think we're, for the most part, ready to finish up this next part and do some practice. I'm going to see you in class tomorrow. We're going to take a little bit of time to go through this and make sure that you are solid on writing ion formulas and identifying them and actually being ready to go. Have a good evening, and I look forward to seeing you in class. Goodbye.